Okay, let's do problem 8.70 of Sonntag. We have a piston cylinder arrangement which contains 1 kilogram of water at the state 1 of 150 kilopascal and a temperature of 20 degrees Celsius. The piston is loaded such that the pressure is linear in volume, so obviously we have a spring arrangement. Heat is added from a 600 degree source until the water is 1 megapascal and temperature is 500 degrees Celsius. So we must find the total heat transfer and the change in entropy. So it's a very straightforward problem, but it helps to elaborate on some important issues. So the heat transfer during this process, Q12 is equal to mass multiplied by U2 minus U1, these are the specific quantities, plus W12, where for a linear system W12 is equal to half of P1 plus P2 multiplied by V2 minus V1 multiplied by the mass, because these are specific quantities and we have to multiply by the mass. So if we take this into account, we can easily find work done with which we can find the heat transfer. So let us first do that. Let us then go to entropy later. So state 1, P1 is equal to 150 kilopascal, T1 is equal to 20 degrees Celsius. State 2, P2 is equal to 1000 kilopascal, T2 is equal to 500 degrees Celsius. So if you want to plot the process on a PV plot, it would look something like, so 150 kilopascal, 20 degrees Celsius. Let us first see where this point can lie. So it is water. So we go ahead and we do the property plot for water. Don't include the lines, so we want to do a PV. Okay, there we are. So 150 kilopascal, so 150 kilopascal is somewhere over here, and okay, we must do it in the PT plot. Let's see if that is available to us. So we do not have any PT plot available. So anyway, we'll see in the end where the points lie, but it is important to know that these two state points are very trivial to find out because all the properties are known. So let's see. Okay, the mass is given as 1 kg. So the Q12 is equal to mass multiplied by U2 minus U1 plus W12, where W12 is equal to 1 by 2 multiplied by P1 plus P2 multiplied by mass multiplied by SP wall 2 minus SP wall 1. This is the area of the trapezoid. Okay, so let us check for consistency between the units. This is in kilojoule, so correspondingly this must also be in kilojoule. This is in kilopascal, this is in meter cube. Therefore everything is consistent. This has to be in kilopascal, which we have taken to be in kilopascals. Okay, so this should give us the heat transfer. Okay, there's some error. Okay, clearly we have not defined the U's and the specific volumes. So U1 is equal to int energy of steam at T equal to T1, P equal to P1. Similarly, SP wall 1 is equal to volume. We just copy the state. Okay, good. do the same for this. Okay, there we go. So let's save the file P870. So most of these files I have put in the Dropbox. The others you should be able to do it on your own. It is only a matter of practicing the problems. Okay, let's see now if this works or not. So the work done. Okay, the heat transfer is equal to 3244 kilojoule. So heat is absorbed by the system because the Q was positive. Q is positive, so heat is absorbed by the system. Work is also done by the system. So if heat is absorbed by the system, so let us come to the concepts from the second law. So the system is absorbing a heat equal to Q12. Corresponding the reservoir, which is always at a fixed temperature of 600 degrees Celsius, is losing heat equal to minus of Q12. Whatever heat is being gained by the system is lost by the reservoir. So the entropy change of the system, what would be the entropy change of the system? If we write the second law of thermodynamics for the control mass, ds equal to del q by t plus delta S gen. But since we know the two states 1 and 2, then we can directly find ds equal to S2 minus S1. If we did not know the state, okay, so once again let us draw the piston and let us draw the heat transfer from a source. So this is equal to Q12, it is losing. So this is the heat addition to system, and minus Q12 is the heat lost by reservoir. So for this control mass, we have ds is equal to del q by t plus del S gen. If we integrate, S2 minus S1 equal to integral del q by t plus delta S gen 1 to 2. But we know that S is a state property. And we have already found out what the states 1 and 2 are. So we know directly what S2 minus S1 are without due information about how Q and T are varying with each other, because to do the integral we need to know how the relationship is between T and Q. Also we don't need to know what the entropy generation is. The manifestation of whatever the integral in the QT plane would be and whatever entropy is being generated would be reflected directly in the form of the two states. The two states are given all directly to us. If the two states are not given, then we had to sort of find out what this integral would be. If we would have been given that it is an isothermal process, then T would come out from the integral and then we would simply have Q12. But in the absence of those informations, here pressure and temperature, pressure and volume are in fact varying linearly. Okay, in that case the temperature will vary differently with Q, whatever Q or locally is going on. Therefore we don't need to know how these terms are varying. We just know the states 1 and 2, by virtue of which the change of entropy of the system is equal to S2 minus S1. But then what is the change of entropy of the surrounding? For the surrounding, it is equal to del q by t plus delta S gen. If we assume that the surroundings are exchanging heat in a reversible manner, then S gen goes away. It is equal to del q by t, which is equal to minus Q12 by T reservoir. So the delta S total equal to S2 minus S1 minus Q12 by T reservoir, where the T reservoir must be in Kelvin. So let us do that. What is the total change in entropy? So we need to also have information about the entropy. Similarly, for the second state, okay, ds12 for the control mass is equal to S2 minus S1. ds of the system for the ds for the process for the surrounding is equal to minus of Q12 divided by T reservoir. The T reservoir is given as 600 degrees Celsius. This should give us the total entropy change so the total entropy change is equal to 3.751. Because the surrounding is losing heat, the entropy of the surrounding is decreasing, but the transfer of heat to the system causes a much higher increase in the entropy of the control mass. The addition of these two leads to a net increase in the entropy of the system, which is consistent with the second law of thermodynamics. One additional concept that I'd like to mention here is that if we have a system and if we have a surrounding and there is some heat transfer between them, if we consider this to be the control mass, whatever heat is being transferred is merely an internal balance. If we write the first law for the control mass, there is no net Q to this control mass. Okay, this control volume receives no heat and is exiting no heat. So for the control mass, the net Q is 0, W is 0. So the manifestation of the second law, so ds system plus surrounding is equal to del Q by T plus delta S gen, but del Q by T for this is by construction 0. Therefore delta S system plus delta S surrounding is equal to delta S generation. So this is the delta S total. The system plus surrounding is equal to the delta S total. Delta S generation should always greater than equal to 0, which in this case is true. Thus the process is a perfectly valid process. We have found out all the parameters that were needed. We found out the heat transfer and we found out the total change in entropy.